Good morning, good afternoon, good evening. We are back again for AI Tech Talk Live, and today we will be discussing custom SoCs for artificial intelligence. This is a live event. We have some questions that came from the audience that we will cover today, and that specifically relates to SoCs for AI. Just as a recap, we have been covering topics on artificial intelligence, and more specifically in the last couple of weeks on advanced artificial intelligence. For the last 3 to 4 weeks, we have been focusing on AI and semiconductor. We are Skive and Robometrics machines. We are specifically focusing on building machines that feel. If you're interested in knowing more, or if you like to invest, or if you like to join us as one of our employees, please feel free to write to me directly via Facebook, LinkedIn, or via email. Okay, let's get started. So I will start with giving a little bit introduction about SoCs, what they mean, so that you have some understanding, even if you don't come from a technology background. We started with general purpose chips. So Intel or AMD is a great example. That was 20 years back. Then we next to the next wave where we have a little bit more focused chips. GPUs from Nvidia is a great example. And now we are at a stage where we are building these chips that are specifically meant or they're optimized for a specific application or for a use case. That's where SoCs come into picture, where these chips are not just meant to be optimized for one specific application. In addition, they also includes a lot more components that needed to make that application or the system work. That's what a SoC is, system on chip. You have the chip, and if you include multiple systems on a piece of silicon, that's what a SoC is. SoC that's very specifically built for AI use cases, application, or systems is AI SoC. That's the focus of our discussion today. And our first question that came from you yesterday was, what are some of the cool examples of specialized AI SoCs? I will start by giving a few examples of, to some extent, not very specialized, but they're still specialized in the sense that they are termed as AI accelerators, or they're using AI in an interesting way on silicon, or they have built ways to make artificial intelligence workload or applications run better using that piece of silicon, as opposed to a general purpose processor like Intel CPU or Nvidia GPU. So the first one I would say is Summernova. They're doing really very well. What they did was they redid the operational hardware to optimize for AI-centric frameworks. And then they developed a system architecture that they claim is flexible, efficient, scalable, and optimized for running some of these AI algorithms on the silicon. It's still a general purpose AI accelerator because it's still specialized. It still is meant for multiple use cases. Multiple use could be used in a camera, in a drone, or in even a data center. The second example is actually from a big company, Intel NPL 1000. What they did is that they have a large amount of HDM RAM or memory and local SRAM much closer to where the compute happens. One of the issues with AI workload is that you have lots and lots of data. You need to process it really fast. And now that the processing power is increasing, you are in a bottleneck. You need to move that data from your memory to the processor really fast. And that's what Intel NNPL did. And as the L said, it's meant for learning, that you could get the data from the memory to the processor very, very fast. So that's the second. The third is Mystic. They have been focusing very much on the edge computing, especially on automotive. They call their chip IPU, and the specialty is that they do matrix multiplication in analog. And they claim that that makes things faster, you have less latency, you also use power much more efficiently. It also reduces the area that's needed on the silicon, and hence any AI workload could run better. The next example would be Cerebras, where they put lots and lots of CPU cores, actually 400,000 cores to be precise, in a piece of silicon. And they obviously have a lot of memory bandwidth. They claim it's 9 petabytes per second of memory bandwidth. And then they optimize some of the ways you could work with these CPUs and so much bandwidth. They call these cores as Cerebras sparse linear algorithm cores. Now, as you saw in the last three examples, we were able to optimize in memory, making the memory closer to the CPU, or doing matrix multiplication. That's the fundamental block of doing artificial intelligence training or even inference in analog, or optimizing the chip to run AI algorithms better on silicon by optimizing the data flow. In Cerebras, they got lots and lots of power on a piece of silicon, which is important if you're doing high compute artificial intelligence inference or training. The last one I would say is NovoMind, that avoids the overhead inherent in other chips that require tensors to be enfolded into two-dimensional matrices. You will hear this thing again, matrices, matrix multiplication. And yes, this is all linear algebra when you talk about artificial intelligence. So if you want to be an AI, you better fall in love with mathematics, especially linear algebra from high school. And NovoMind, by not requiring these matrices or tensors to be unfolded into two-dimensional arrays, makes the computation faster. So that's one level of general purpose chips. The second level is where these chips are not AI accelerators per se. They're very specialized for one use case and one use case only. Tesla FSD chip is a great example. FSD means full self-driving chip. It was previously called Autopilot Hardware 3.0, and now it's called FSD. I like the name actually compared to Autopilot Hardware 3.0. It's an autonomous driving chip designed by Tesla, and it was introduced about 2 years back. And Tesla claims that it is aimed at autonomous level 4 and level 5 driving. Level 5 is with the car drive itself. There is no car as of today available that is level 5. The most we have gotten to is level 3, and to some extent on level 4. Waymo claims that they're working on level 4, but we don't have level 5. They still use some of the cores that are similar to what you will find in other specialized CPU. They still use the Cortex A74 cores from ARM, which operates at about 2.2 gigahertz. But the most interesting part is that it's a system on chip. Everything that's needed for self-driving is there on that one piece of silicon. Another interesting fact about how these chips are being used in a Teslas that's available today is that instead of one of these FSD chips, you will actually find two of these SSD chips per car. And the reason is not because they have larger computes, though you need two chips, but because of redundancy. You don't want your autonomous car to crash or to stop in the middle of the street on the highway because your CPU burned out. That's where they have redundancy. This is similar to what you will find in an aircraft today, where you have a backup, and in some cases you have backup to a backup. The second example that a lot of you are always using and familiar is the A14 Bionic chip that goes into your iPhones. It's based on a 64-bit ARM processor, It's designed by Apple, manufactured by TSMC in Taiwan. It is there in your iPhones, it's there in your iPad, it's there in your various other Apple devices. These two chips, A14 Bionic and Tesla FSD, are a great example of the world we are going towards, where we are coming to more and more specialized chips built by these companies itself. Next question. What is driving the trend of these custom built SoCs as opposed to using chips from Intel, Nvidia, and AMD? I've actually touched upon this a little bit. And the answer is one word: TSMC. A couple of years back, it was just not possible for a small company or even a big company like Facebook or Tesla or even Apple to have their own custom built silicon. It was expensive, and then there was no foundries available which could actually do that. But that has changed in the last 5 to 10 years. Now, the top foundries in the world are Intel, Samsung, and TSMC. TSMC and Samsung account for about 70% of the silicon build in the world. And TSMC specifically have these processes set in such a way that they have been able to work both with startups and big companies to build their own custom silicon at a very low cost. And that is, I believe, the biggest factor that's driving these custom ASICs, that whether you're a small or whether you're big, you can build your own custom built SoC at a small cost, as well as as nominal scale. You don't have to order, let's say, 1 million chips. Our third question is, why go through the pain of building a custom SoC? And that's a great question in the sense that why did Tesla ditch Nvidia and came up with their own silicon? Why is Amazon now also have their own piece of silicon as opposed to going through using, let's say, Google TPU or Intel or Nvidia or AMD? And the reason being that they can do it. That's one. From a business perspective, it makes a lot of sense to be self-dependent as opposed to be dependent on a third party for a very core functionality of a data center or for your products. As we are seeing right now is that there's a chip shortage in the world, and not long back, U.S. had sanctioned some of the nations, and that resulted in one of the biggest phone manufacturer going down. You don't want that to be happen, so you need to control the supply chain, and that's one of the biggest business reasons to be building your own SoC. And by the way, traditional vendors like Intel has not been great when it comes to quality. We have seen so many bugs and issues coming on Intel x86 architecture. Secondly, from a technology perspective, if you are building a SoC for a specific application, for a specific architecture, you could optimize as much as possible for latency, for power, for a compute per watt, and more important, you could secure it in a way which is acceptable to you. The world is in a point where the world, I believe, is getting more and more divided. It is also becoming a lot more insecure, as we saw with the big SolarWinds hack last year. Security, either at the system or the hardware level, as well as at the application level, both are extremely important. And that's where our SoC could actually help. If you put everything on a piece of silicon, it's much more harder to reverse engineer by anyone. It is also easier to make the silicon secure, and hence the application or the system where it goes into. Okay, folks, that's the 3 questions we had today. We'll be back next week, same time. And just a reminder, we are live on Clubhouse. We will be here on Facebook as well, so please feel free to reach out. And as a reminder, we are hiring, so happy to hear from you. Thanks. Bye for now.